In the previous video, I presented the discretionary access control policy and its implementation from a rather theoretical point of view. Actual DAX systems are not all the same. For example, there are differences between the Unix DAX system and the Windows DAX system, between the Unix DAX system and the DAX system that is used in SQL databases. In this video, as a case study, I will present one DAX system, which is the Unix DAX system. So, like most operating systems, Unix is an access control list-based system. Unix uses groups to shorten the number of entries in an access control list. And a group associates a group name with a set of users. A user can belong to several groups, with one group being the primary group, that is the default active group at login. And the user can change his active group at any time. Each file is associated with exactly one group. So it may seem a bit strange and restrictive that each file is associated with a specific group, knowing that a group represents a set of users. Why would a file be associated to a given group? So this will clarify gradually while we present the Unix DAX system. But you must be aware that the Unix DAX system was designed at a time where the computer resources were scarce. So in fact, the Unix DAX system is not the most intuitive DAX system, but it is computationally efficient and requires few storage resources. A unique user ID identifies a user, and a unique group ID identifies a group of users. Each file has an associated access control list, an owner ID, and a group ID stored in the file's inode. You know that in the Unix system, inodes are data structures implementing the file and its metadata, like the access control list. And of course, since we are in a DAX system, only the owner of a file may change the access control list of that file. In fact, the access control list of file F defines three sets of privileges. The owner's privileges. I refer to them as P-owner of file F. And I will use this notation in the next slides. The group's privileges. That is, the privileges of the users who are not owner of file F, but member of the group associated with file F. I refer to them as P-group of file F. The others' privileges, that is, the privileges of the users who are not owner of file F nor member of the group associated with file F. I refer to them as P-other of file F. Unix employs three identifiers, R, W, and X, for designating file access privileges. R stands for read, W stands for write, and X stands for execute. On this slide, we listed the contents of the current directory. It includes one file whose name is service and one subdirectory whose name is datadir. Let's focus on file service. Owner of that file is Bob, and group of that file is staff. Bob, as owner of file service, has full privileges on it, that is, read, write, and execute. So at this point you may ask, why do we need to encode this? Indeed, since Bob is the owner of file service, we know that he has all privileges on it. Yes, it's true. But Bob is a security administrator for his own files. So he may decide, for example, to disable, at least temporarily, his write privilege on file service, if it doesn't need it to modify the file. Do not forget this important principle of least privilege, which I talked about in a previous video. Members of group staff have read and execute privileges on file service. And other users simply have the execute privilege on file service. So I told you that each file is associated with a unique user ID, which is the ID of the owner of the file, and a unique group ID, which is the ID of the group of the file. On this slide, we can see that the owner ID for file service is 100 and the group ID is 8. I said in the previous slide that R means to read, W means to write, and X means to execute. That's true. However, the semantics of these privileges depends on the resource. For example, privilege R for a file means the privilege to read the contents of the file. For a directory, it means the privilege to list the file names of the directory by using the ls command. Privilege W for a file means the privilege to modify the contents of the file. For a directory, it means the right to create, delete, or rename files in the directory. Privilege execute for a file means the privilege to execute it. For a directory, it means the right to traverse the directory, that is, to access to files and subdirectories. This means that you cannot execute a file if you cannot traverse its directory, even if you have execute privilege on the file. And there are also other types of resources, some special files, for which the semantics of these three privileges will also be a little bit different. So what I have presented so far is the basic system of Unix access control lists. This system does not provide security policies with high expressive power. With that system, the security policy cannot refer to a specific user. For example, Alice cannot define a rule saying that Bob, and only Bob, can look at her pictures. So in recent versions of Linux, this default basic access control system can be replaced by the so-called rich access control list system. So I will not introduce the system. I will only mention that this rich access control list system allows to express a security policy with a better granularity. And better granularity means that the security policy can address specific users and includes additional privileges, in particular different types of write privilege. In the first part of this video, I presented the access control list part of the Unix DAX system. This access control list scheme has been used for many years in all Unix systems throughout the world. However, this system has some limitations regarding the expressivity of the security policy. That's why a more advanced system, the rich access control list system, has been included in recent versions of Linux. In the second part of this video, I will present the access control algorithm of the Unix DAX system. That is the algorithm that the security kernel uses to decide if a specific access to a specific file requested by a specific subject should be granted or denied, given a security policy expressed in terms of access control list. You know that when a program executes, it becomes a process. And generally that process inherits the privileges of the user who created the process. So how does this inheritance mechanism materialize in the Unix system? It materializes as follows. Each process running on behalf of a user will have an effective user ID, equal to the ID of that user. and it will also have an effective group ID equal to the ID of the active group of that user. And the pair effective user ID and effective group ID defines the so-called protection domain of the process. And this concept of protection domain is important since it implicitly defines the privileges held by the process. And this set of privileges is the union of three sets of privileges. The set comprising the owner privileges of each file F having an owner ID equal to the effective user ID of the process. The set comprising the group privileges of each file F having a group ID equal to the effective group ID of the process. And the set comprising the other privileges of each other file F. So, knowing what I have just said, we can now specify the access control algorithm. So, let U be a process attempting to access file F with privilege P, P being read, write, or execute. File F is recorded in directory D. So we have the effective user ID and the effective group ID of the process, defining its protection domain. And we also have the user ID and the group ID of file F, that is to be accessed by process U. Access is authorized if any of the three following conditions holds. So the first condition says that if the owner of file F is the user on whose behalf the process runs, and if privilege P is included in the owner privileges of file F, then access is granted. The second condition says that if the owner of file F is not the user on whose behalf the process runs, and if the group of file F is the effective group of the process, and if privilege P is included in the group privileges of file F, then access is granted. And the last condition says that if the owner of file F is not the user on whose behalf the process runs, and if the group of file F is not the effective group of the process, and if privilege P is included in the other privileges of file F, then access is granted. So this access control algorithm looks simple, but requires a little bit of thinking, so do not hesitate to pause the video until you fully grasp it. Please note the following. Accessing file F requires first being able to traverse the directory D where file F is recorded. So the algorithm should apply on the directory D first, and even in a recursive way possibly to the parent directory of directory D. If execute access to directory D has been granted to process U, then we can check if process U may access file F with privilege P. So we said earlier that each process running on behalf of a user with user ID UID and active group ID GID will have its protection domain equal to the pair UID GID. It's true that most of the time the process will run on behalf of the user who created the process. However, there are exceptions. In fact, each file comes with two special bit attributes under the control of the owner of the file. And these two special bits are called the setUID flag and the setGID flag. So let's see the use of these special flags. If the owner of a program has set the setUID flag of that program, then any process created from that program will run on behalf of the owner of the program, regardless of the user who created the process. And if the owner of a program has set the setGID flag of that program, then any process created from that program will run on behalf of the group of the program, regardless of the active group of the user who created the process. So here we can see that Bob has set the setUID flag and the setGID flag of program service. When these bits are set, there is an S instead of an X in the directory entry of the program. So this means that the protection domain of any process created from file service will be the pair UID GID of file service, regardless of the user who created the process. Let's clarify all of this with a few examples. In this first example, Alice runs the program called Service owned by Bob. Alice's active group is Student. The group of file service is Staff. What will be the protection domain of the process created from this program? Well, since setUID and setGID flags are not set, then the protection domain of the process will be the pair UID of Alice, GID of Student. That is, the process inherits its privileges from the user who created the process. So this is the same example as before, but this time Bob has set the setUID flag of file service. What will be the protection domain of the process created by Alice from this program? Since setUID flag is set and not the setGID flag, then the protection domain of the process will be the pair UID of Bob and GID of Student. That is, the process inherits its privileges from the owner and from the active group of the user who created the process. This is again the same example, but this time Bob has set the setUID and the setGID flags of file service. So what will be the protection domain of the process created by Alice from this program? Since setUID and setGID flags are set, the protection domain of the process will be the pair UID of Bob, GID of staff. That is, the process inherits its privileges from the owner and from the group of file service. So setUID flag is very often used to allow a program owned by root to be executed by standard users. It is by far the main application of the setUID flag. For example, commands like password or ping, which are both owned by root, need root privileges to work properly. So they have their setUID flag set. So in the second part of this video, I presented the access control algorithm of the Unix operating system. I think you are starting to realize that the Unix DAX system is not as simple as you might think. And in fact, fully understanding the Unix DAX system requires mastering a lot of things. It requires mastering the interactions between the permissions set on the directories and the permissions set on the files, which are contained in the directories. It also requires fully understanding the effects of the setUID and setGID flags. And this is not finished. In the last part of this video, I will show you that processes can change their protection domain. And I will also address the Linux system of capabilities. Yes, you have heard well. A system of capabilities. Linux is mostly access control list based, but it also includes a system of capabilities. So In fact, a process has more than the effective UID and the effective GID. A process has also a real UID, a saved UID, a real GID, and a saved GID. So what are all these IDs? Why all these IDs? So I will come to this in the next slide. But before that, let me just tell you that if you need to see all the IDs associated with a process, you can type the following command. So now, what are all these IDs associated with a process? First of all, the only IDs which are used for access controls are, as we said it in the second part of the video, the effective user ID and the effective GID. They are the main ones. They define the protection domain of the process. Now, let me talk only about real UID and saved UID. The real UID identifies the user who created the process. If the setUID flag is unset, then real UID and effective UID are the same. It's only when the setUID flag is set that they can be different, if the user who created the process is different from the owner of the program. A process may change its effective UID to real UID, allowing a change in its protection domain. And the previous effective UID is not lost since it was saved into the saved UID. And later the process might set back its effective UID to the saved UID. So you will understand with examples. At that point you must remember that real UID and saved UID are to allow a change in the process protection domain. And the same reasoning can be applied to effective GID, real GID, and saved GID. So, this example will show you how a process can change its protection domain and why. So, consider the ping command. This command uses the setUID flag to run as root. Why does the ping command require root privileges? For opening a raw communication socket. Opening a raw communication socket requires root privileges. Now, let us suppose that Alice runs the ping command. The effective UID of the created process is the UID of the root user, since the setUID flag is set. Now, Alice created the process. So the real UID of the process is Alice's UID. If the ping command is well designed, if the ping command has been designed according to the least privilege principle, it should drop root privileges when it no longer needs them. And the process can do this by setting the effective UID to the real UID. The process has temporarily dropped root privileges. Why temporarily? Simply because the now unprivileged process can change back to root by setting its effective UID to the saved UID. So this is exactly the same example, but the process sets the saved UID to the UID of Alice when changing its protection domain. Here. Okay. So because of this, there is no way the process can change back to root. In that case, root privileges have been permanently dropped. So we already said it. Programs with setUID flag set are very often programs owned by root to allow regular users to perform certain tasks requiring root privileges. However, If a program with setuid root is vulnerable, then the security of the entire system can be compromised. Yet, the fact that programs can change their protection domain and permanently drop root privileges is the first step to mitigate the risk of using a program with setuid root. But still, there is a risk. So, to reduce the use of programs with setuid root, a system of capabilities has been introduced in recent versions of Linux. So let's have a look at these capabilities. So there are almost 40 Linux capabilities, each corresponding to a specific root privilege. For example, capability capnet row gives a process the right to open a row socket. So let's use an example to explain this system of capabilities. First, I will, as the root user, unset the setuid flag of the ping program. So this is the command to unset the setuid flag. I am the root user and I unset the setuid flag of command ping. You can verify that the setuid flag is unset with this ls command. Now, if Alice tries to ping an IP address, she will face the following error: socket operation not permitted. Opening a socket requires root privileges or the specific privilege capnet row. So let us simply add the capnet row capability to the ping command. I am the root user and I am now applying the capnet row capability to the ping command with the command setcap. Alice can now use ping normally. So I hope you have understood. The ping program is no longer a setuid root program. Alice executed it. The created process ran on her behalf. That is, its effective UID was equal to Alice's UID. And the process did not fail since it possessed the capnet row capability. This figure illustrates what I have just said. The ping program is no longer setuid root. If Alice runs it, the created process holds the capnet row capability. If you have access to a Linux computer as the root user, you can easily reproduce this experiment. Linux capabilities are applied to executable programs and then inherited by the processes generated from the executable programs. And by the way, these capabilities are stored as metadata, like the access control lists. That is, in the inode of the executable program. The consequence of this is that any user running the ping command will generate a process holding the capnet row capability. So in fact, this capability system does not follow the definition of the capabilities we gave in the previous video, where capabilities were linked to users and then inherited by processes created by users. You remember the decomposition of the access control matrix. Here, the capabilities are applied to programs and then inherited by processes created from these programs. So because of this approach, I cannot easily implement a security policy saying that only the root and Alice are allowed to use the ping command. In fact, this Linux system of capabilities is more of a patch to reduce the use of setuid root programs than a real system of capabilities. This is my opinion. I do not know if it is shared by more experienced Linux users than me. So this slide shows a small recap of the Unix admin commands relating to the Unix DAX system. Change mode for setting access control list permissions and setuid and setgid flags. New group for a user to change his active group. Change owner to change the owner of a file. Change group to change the group of a file. You also have commands to deal with rich access control lists. And finally, the setcap command to apply a capability to an executable file. Setcap is a command reserved for the root user. So in this video, I presented the Unix DAX system. I presented the Unix access control list, the access control algorithm, the concepts behind the setuid and setgid flags, the protection domain of a process, and the Linux capabilities. I didn't go into details, and I didn't talk about everything. For example, I didn't really present the rich access control system, the rich access control list system. I didn't talk about the effects of setting the setuid flag and the setgid flag on a directory. I didn't talk about the sticky bit, which is another security flag. Finally, I superficially presented the Linux capabilities. My aim was simply that you could get an overview of the Unix Linux DAX system without getting lost into too many details.